Welcome back to the channel. Hope everybody's doing well. And in today's video I thought we'd start back to front with this one. This is showing the results of my little work, and then I'll go into the how and why after this. What I've done is built up a little 2-to-1 voltage divider, so I can use that on an input to an oscilloscope to capture signals from a generator whilst it's online. At this moment in time I'm using the Regal D1022 in arbitrary waveform mode to generate an example of the signal. That's actually too low. Out on site the signal is coming in at around about 46 volts. So to do that I've got a power amplifier at the back here that the Regal is feeding into, and then the output is coming out of the power amplifier. This first one is the raw signal, and the second one is through my voltage divider. So you can see here this top signal is 46.6 volts, and measuring on the input I've got 23.4 volts from my voltage divider. Because my voltage divider is 2-to-1, I can cheat a little bit and change the probe as a 2 times probe, get rid of that, and then we are 46.6 volts against 46.8 volts. So that's what I've produced. I'll get this out of the way and we'll look at how I designed and built it. Now we'll go through the design of the voltage divider. I've said at the top here I want a 2-to-1 divider, effectively halving the input. So for my 40 volt signal going in, I want 20 volts coming out. Over here on the right, this is the divider circuit that I've got with divider A resistor and divider B resistor. So for my 40 volts across those two resistors, I want 20 volts to come out here and go into the input of my oscilloscope. So what you now have to consider is that this oscilloscope has its own input impedance. You can find that out from the data sheet for your particular scope, or you can just put an ohm meter straight across the input and you can measure it that way. But generally speaking, oscilloscopes are around about a 1 mega ohm input. So this 1 mega ohm will actually be in parallel with the divider B resistor here and will consequently affect the ratio. And we see this over here, this top table that we've got. These are my theoretical values. So I've decided that A will be 100 kilo ohms, and then I've put the scope input there of 1 mega ohm in, and then I can play about with the value for divider B to get me the correct ratio voltage coming out. So the divider B resistor and the scope input are in parallel, so I have to do the reciprocal of them to get the parallel input value. That'll give me a divider ratio, and then you can see here for 111.1 kilo ohm divider B resistor, divider A resistor is 100 kilo ohm. I end up with a 20 volt output going into my scope. Over here you can see I've done a little check on the power going through the resistors, so that will be my current going through the divider network there, and then that will be the power dissipated by the resistors, just to make sure that I select resistors of the correct wattage so that they don't overheat. The 100 kilo ohms, that's just the standard starting point that I have. It's just chosen that so that I don't load up the signal too much, and obviously I don't put too much power through the resistor as well. So it's dependent upon the voltage I've got, but also the type of sensor you got. If you make these too low, you may affect the actual output signal from the sensor and disrupt it. So you do need to be careful of that, but I generally start off around about 100 kilo ohms. This middle table here, all I've done is with a box of resistors and measured them and fed exactly the same calculations, just with the actual resistance values that I'm measuring, and then I can see how close I can get to my ideal voltage ratio. And then at the bottom here, this is after it's all been put in the case. I just carry out the measurements for divider A resistor, divider B resistor, and then I can get my ratio. And that data there will go into my calibration software, so I can check this divider on a routine basis, just repeat those measurements and make sure that they've stayed within a plus minus 2% tolerance or something like that. That's just the nature of the business that I work in. I need to be seen to be calibrating the equipment that I'm using so that there's guarantee that it's functioning correctly. You don't have to send this away. I won't send this away. I'll just do this with a standard ohm meter I've got, but I will make sure that that ohm meter does have its own calibration. And that's all the design there, so we can move on now to see what it actually looks like in practice. So this is what it ends up looking like. I like to put them in these little BNC project boxes or BNC test boxes, they call them. This particular one here is from RS Components, but it's now obsolete. I found this on eBay. The only one that RS Components currently do is this one here, which retails for £60. There's an awful lot of money really for what it is. And then there are other versions out there. I did find this one once. I can't find where I got this from, the manufacturer or anything, but this is probably my favourite kind of design. It's much smaller and compact and easier to utilise, but couldn't find them, so I found this. This was actually on eBay. There's a bunch of these being sold, I presume ex stock from RS Components, and it only cost me £20, so still quite a lot for what it is, but it's a bit cheaper than the RS alternative, and it's quite easy to get into, this one actually, so get into that way. Here's my little divider bridge inside, so we come from here, the signal will go onto the input here, and it will come through this bottom resistor, which is soldered onto the outlet, and this will go to my oscilloscope. And you can see here I've then got the tie in there, the T of the bridge there comes in. This is two resistors in series, so that I get the correct value. If you really wanted to get really accurate, you could replace one of these resistors with a potentiometer and then adjust it to suit. But I didn't need that level of accuracy for this, so I was quite happy with this design here. And you can see I've just put some heat shrink over the two resistors there, so that they remain isolated from the rest of the junction there. And doesn't get anything tracking over, not that it would over 40 volts. And then we put them in there and put it back together. The only disadvantage to this is these are really small little nuts, or for what I work in, they're quite little small nuts, and they need a 5mm spanner, which is an unusual size spanner. Almost getting into the realms of radio controlled cars and protection relay systems as well, really, for that size spanner. But we can put them up there. That's all done. That's my little project box all finished. So I can test them with the Picoscope to make sure that it does all work correctly. So here we are, all set up, testing it out on the Picoscope. We have that down in the bottom here. You can see there's my probe going on to the input there, and putting that out of the way there. Unfortunately, it's just out of picture. Same Regal generator set to arbitrary waveform. I'm using my power amplifier, and you can see here I've got this all set up on Picoscope. I now have 40 volts on the channel, so I can get my measurements. I can add in a measurement. What I like to do when I'm measuring these signals is measure the peak-to-peak voltage and plot that against the generator output and the field voltage and field current of the generator as well, so I can see how the signal is doing, and also I can look to see if there's any noise on the signal, if there's any degradation in the actual signal. I do have a proper AGSC, air gap search coil, or flux probe some people call them. I do have a proper analyzer for it, but that applies a load of filters and you don't get this raw data out that you can see in here. So this is why I like to capture it with the Picoscope. And you can see I've got a voltage measurement down there for around about 49 volts is averaging out, so I can record that, and that all seems to be working fine. I'll just show you very briefly what else I have to do. I've set this to a ×2 probe, so that's a probe that I've made up myself within the library. If I set this to ×1, you can see I now only get a 20 volts maximum on the signal. I lose that 40 volts, and if I just quickly drop the divider box off and put this on, you can see I end up with overrange and I don't get a maximum reading down here at the bottom, or the average either, for the peak to peak. So that's why I need the actual voltage divider to enable me to get this to work. And what this also allows me to do, if we go back to our ×2 probe on there, and we can go to 40 volts. Now the reason why I like to use Picoscope as opposed to something like the tablet scope, the mixing tablet scope that you saw earlier, is the mass capability of the Picoscope. So within this you can see I can very easily create the plus or minus 40 volt range to 2 times probe, which I could do with the Mixig. But if I go over on here, I have a couple of mass channels that I have made up. So we can go to this adapter here, and so the way you analyze this signal is that you compare these two halves. You take the second half, you flip it and invert it, and then you compare it, all these peaks, to the first half, which is what you can see is happening here. And then if there's a damage to the interturn insulation on the rotor, because this is what a flux probe does, it looks at the interturn insulation on a rotor winding, and if these peaks don't match or have over a 3% differential, then it's an indication that you've got damage of the interturn insulation and you may have problems with your rotor. So I can very easily create that formula within Picoscope, which is rare that you can do that in some of the other scopes. You really need a really advanced scope to be able to do this, but Picoscope has this all built in, so you can very easily do that. Go to 0 there, and then the other one I have is a comparison waveform as well. Okay, and then that's the one that I need to drag down lower. So this is subtracting those two waveforms, and you end up with this waveform here. You can see there's a fair bit of messing around in here, but that's fairly normal for an oscilloscope signal, really. What I can do is see if the filtering makes a difference. So yeah, we can add filtering onto that, and then you can clean it all up and you get a bit of a waveform, and you see, remove all the interference that you can see in there. That's what the analyzer actually all does, but you don't want to do that all the time. Sometimes you want actual raw data to give you a better indication of what's going on. So there you have it. That's this video on this little adapter box that I've made up. Something slightly different. Hope you found it useful. Thanks very much for watching, and I'll see you again in the next one.